Hi, how are you all doing today? Welcome to this session on building accelerated applications with Vitis. This session is really going to take us about 2 hours. It's really kindly sponsored by Xilinx, and although you can't see them today, we have a few people from Xilinx on the webinar as well, and they'll be joining in and helping answer any questions and queries that you may have. So today we're going to run through looking at how we can build these accelerated applications with Vitis. Hopefully you've all received the instructions for the lab and the slides as well from my GitHub, from the email that came out earlier on. And what we're going to do today is we're going to take a look at this. We're going to run I'm going to talk you through a few slides. I'm not going to give you death by PowerPoint, but I've got a few slides to talk about the concepts and the techniques and the tool itself that we're going to be working for. And then what we're going to do is we're going to take a look. We're going to do some live applications. We're going to do a couple of live labs that you're going to follow along with. We'll probably take a quick 5-minute break around the completion of the first lab, just for a comfort break. I see everybody's found the chat window, which is really great. Feel free to ask any questions, put any chat in there. We've also got a questions window as well, so people can ask questions in there. So as we're going through this, please feel free to ask questions, and we'll address them as that comes up. So without further ado, we'll get started, and we will take a look at what Vitis is and how we can build these applications with it. So I'm sure you're aware now actually that Vitis, it's a tool that Xilinx released maybe a couple of months ago, now, and it's a unified software development environment. And what it does is it unifies what was previously SDX, SDXL, SDSoC, and SDK into a single tool. And it really is quite a powerful development environment, as we're about to see. It's a really good system, and it's really useful in our applications. Now, we can use it in both the edge and at the cloud. So if we want to develop for edge applications that are using Xinx or Xinx MPS SoCs, or even microblazers within just traditional programmable logic, we can use Vitis to develop that. And we can also use it to develop our cloud applications, our increasingly popular applications targeting Alveo cards or the Amazon Amazon F1 instances. So it's really quite a good tool. It's going to give us a lot of applications. And we're going to learn a lot about it today. Now, it supports 2 flows. It actually supports what's called an embedded flow, which is the traditional embedded software development. So that's the creating software for your Xinx MPS SoC, your Xinx, or your microblaze. And it supports the more exciting, what we're going to talk about today, the more exciting accelerated flow. And that accelerated flow actually is what's really powerful to us in actually moving forwards and being able to leverage the power that comes with programmable logic and that really truly parallel capability, and allows us to leverage that. So Vitis really provides all of these, and to do this, it gives us a number of layers that we can work from, which is really important. So that's going to be the really important thing that we're going to run through. We're going to take a look at this, and you can see it runs through in a number of layers. So we've got the AI, we've got the AI level that we're going to take a look at, and today we're going to end the lab with the Xilinx DPU up and running into the hardware, and we're going to show you how to do that. We've also got another layer beneath that, and that allows us to have the Vitis accelerated libraries. And we're going to take a look at these accelerated libraries and run through there, because we've got a series of libraries that really do help us accelerate these applications. So we don't have to start from scratch. We can start running through with the libraries, and we can start building off them. Of course, actually, what we need as well is the Vitis co-development kit, and that gives us everything we need really to do the embedded and the edge application. So it gives us the compilers, the analyzers, the debuggers, and then obviously we've got the Xilinx runtime, which we're going to take away and explore. And then finally, of course, we've got this Vitis target platform, and our Vitis target platform is going to be either an edge board like the ZCU104, the Ultra 96, or a cloud application such as the Alveo cards. So let's take a look now at a little bit more at where we're going and what we're doing. We can start really starting at the top. We have this AI development environment, and that's really allows us to accelerate AI inference applications both in the edge and the cloud. And to do that, we can work with the really popular frameworks that come from the with the tool. So we can work with Caffe, we can work with PyTorch, we can work with TensorFlow, and we can use those really common industry standard frameworks to create applications and to drive them forward, and to work this through the Vitis AI and get it into the Xilinx DPU and give us a really good high performance application that's gonna give us really ground-beating sort of inference technologies. And I'm going to show you how we can do this today. As part of the second lab, we're going to run through that, and we're going to show you how to do that. So we have this Vitis AI, and like I say, it works with Caffe, PyTorch, TensorFlow. The Xilinx are also really good. They provide the model zoo as well, so you can see a model zoo with all the networks that you might want to use for your applications. And then actually within the Vitis AI development kit itself comes everything that we need to be able to compile from those frameworks using either the model zoo or custom models to actually be able to compile the network, to be able to quantize the network, and to optimize that network as well. And that's really powerful, because when we're working within the programmable logic world, we really want to work with a fixed point representation and not a floating point representation, because we can really leverage that parallel capabilities using the fixed point capabilities than using the floating point. So that's those three tools: the compiler, the quantizer, and the optimizer. They're going to give us that ability to go from there into the programmable logic. Once we've got our application in the programmable logic, obviously we might want to optimize and fine-tune and make it work better. And that's where the AI profiler comes in, and that allows us to profile our application so as we can tweak, test, and we can manipulate and get our performance just that little bit better. Of course, because we're running on the Vitis environment, we're running with OpenCL, we've still got the Xilinx runtime in there that's managing, and we're going to look at the runtime in a couple of slides time, but essentially the runtime is managing the management and the loading of the programmable logic, the transfer of data between the processing system and the programmable logic, and then obviously we've got the deep learning processor, which this is all running on. So it's quite a good, powerful technology stack there that we've got to help us with this. Now, like I mentioned a little while ago, we have a range of accelerated libraries, and the reason why we have these libraries is that we don't just want to, if we start developing our new applications, we start wanting to leverage that acceleration capabilities using OpenCL. We don't want to have to start from scratch and start writing all the functionality that you have into and do it all again from scratch, because it's not productive. The benefits and the time you save within using the higher level language you lose because you have to rewrite all the libraries. So Xilinx are really great, and they provide us these accelerated libraries. And you can see the libraries are actually split into two elements. You'll find the first set of libraries called the common libraries. Now these just contain standard standard functions, standard libraries that any application might want to use. So they contain math libraries, they contain linear algebra, DSP, data management, the very basics of what you might need in your application. We also have what they call domain-specific libraries. So these, if you're working in a particular domain, maybe you're working in the vision and the image processing domain, or maybe you're working in the quantitative finance domain, And there's a range of actual acceleration ready functions that are there that you can pick up and start working with today. And what you'll find if you take a look at the libraries, maybe if we run a little bit of ahead of time, I'll show you a little bit more about these libraries. But what you'll find is these libraries essentially are coming 3 levels: level 1, level 2, and level 3, in terms of complexity and ease of support and pulling them into your application. So there's a really quite a flexible, powerful set of libraries there that really allow you to hit the ground running and focus on your value-added activity, and not just on having to create the bare bones and recreate the existing functions that you might want. Now, within the core development kit, and this is really what we're going to look at a lot today. What I'm trying to do today is give you all the capabilities, the understanding, so as you can see, so as you're confident of firing up the tool, of installing the tool, of opening a new project, of running through the elements of the design of that project, and then of being able to optimize and deliver that and deliver something out of that project into your customers or into your internal development teams if you want to. So this core development kit, it gives us everything we want to do, and it's really quite exciting because we get a GUI if we want. And today, obviously, I'm going to be using the GUI because it makes it a lot more interactive to show what's going on. But if we want, we can use command line tools, we can script them, and this gives us everything we need to do compilation, to do debug, to do analysis of these C, C++, and OpenCL designs that we're going to work for. So it's really, really quite powerful. And in our first lab, we're actually going to take a look at how we can do this debugging, this emulation, this optimizing, and running through. Now, what makes it really interesting is you can use the integrated GUI if you want. You know, you can use the integrated GUI, which is based on Eclipse and will look very familiar to you if you've ever used any of the previous Xilinx tools. But you can also, if you want to, you can also pull it into your, because it's really pretty much open source, you can pull it into your own preferred GUI as well. So if you like VS codes or something, you can pull it into that. And of course, this GUI, this core development kit, is the one that supports both the embedded and the accelerated flow. So one of the things that we've got as well is we want to talk about these the target platforms that we're going to be targeting for Vitis. And I've mentioned previously, you know, we're going to be looking, and we can target the embedded world. So we can target the SoCs, the MPSoC, the RFSoC, and the Zinc, or maybe we can target microblazers as well. And in the cloud, we can go for these Alveo and these AWS F1 instances. Now, what's really what I like a lot actually about Vitis is you can switch really easily on your targets between whether you want to go for the cloud or whether you want to go for an edge application, and it really does build that up quite quickly. But it also creates everything we need. All the files, all the boot files and everything are needed. And as you'll see as we progress through this, you'll see that we're creating everything that's necessary and might be needed. So we're going to be creating all the boot files, we're going to be creating SD card images, and literally everything we need to hit the ground and start running. So I've mentioned the Xilinx runtime a few times, and that's really I guess the best word for it, I guess, is the secret that brings it all together and binds it all together. It's kind of like the Force if you're a Star Wars fan. It binds everything together. And it gives us this ability to communicate between what we would traditionally call a host and an accelerator. Now, we're going to talk, these terms might not mean a whole lot to you, but we're going to talk a little bit more about this in a few slides' time. But essentially, the XRT enables the communication between the host and the accelerator. So when we're talking about the host in the Xilinx world, we're talking about a x86 if we're in the cloud, or we're talking about an ARM A9 or an A53 within a Zinc MPSoC. And of course, the accelerator is always going to be in the programmable logic. That's going to be there. And what the XRT does, it gives us all the libraries, all the APIs, all the drivers, all the utilities, everything we need to be able to do the entire life cycle management of the accelerators in our programmable logic. So it gives us the ability to download the programmable logic, to transfer data, to synchronize, to actually execute the functions that are in the programmable logic. And it really does pull everything together and hold it all together. So this XRT is really quite important. And you'll have installed it if you follow through the labs that I've created to actually install Vitis on your machines to follow along with my labs, then you will have installed the XRT. It's one of the first few steps you do when you want to get it up and running. And here's just a simple example of it actually up and running. You know, it gives us all that ability to manage everything. So not only are we able to download the FPGA binary and do the memory management, but we can also do board management and check the execution management. So in that little image there, you can see actually the Alveo card that is in my machine I'm doing this presentation on. You can see the Alveo card status being checked, and you can see it running through and checking that the Alveo card's all correctly installed and is hopefully going to work there. So we've got a number of elements to Vitis that we want to work with. And the number one element that we need actually in this is we need a platform. So if you think back to when I asked you to install Vitis on your machine, one of the first things we've done, we went away, we downloaded the Xilinx, we downloaded Vitis, we installed Vitis, we went away, we installed the Xilinx runtime, and then the next thing we did was actually go away and install the Xilinx platforms. And for this example, I actually showed you how to download and install the ZCU 104 example, but it's simple to do the same for the Alveo or the Ultra 96. And these platforms are really quite exciting. And what they consist of is essentially two elements. If you were to open up a platform and look at the platform on your computer, what you'd see is two elements. You would see a hardware element and a software element. Now, in the hardware element has been created in Vivado. And in that hardware element, what you're going to see in there is all the AXI connections, all the clocks, all the interrupts, and all the design in the programmable logic that you want to include in that platform and that you want to make available to the Vitis compiler. So when we create our hardware element, we're declaring elements. So we're declaring AXI master and slave ports, clocks, interrupts, and we're declaring those as available to the Vitis compiler. So the Vitis compiler, when Vitis goes away and does its compilation, it's got something it can actually connect to and start working with and start implementing the accelerators using the high-level synthesis, as you'll see. So that's gonna run through, and that's in the hardware element. Now, obviously, the world's not hardware. Actually, the world is increasingly software, and we need a software element to actually pull through and do that. And that's where the software element of this comes in. And this provides the simple boot element to it. So it provides the first stage bootloader, it provides U-boot, and it provides the ARM trust zone, and all the necessary support for the Xilinx runtime that's required, and for QEMU as well. Because as you'll see in our lab when we get started in a little while, we're actually going to be using QEMU as part of our emulation flow, as part of our hardware and software emulation flow. We're going to be using QEMU to run through this. So it should be really quite good, and gives us this ability to do it. And the Linux machine as well, so the Linux element as well, that pulls in we need a file system, so a root file system, and we need a kernel image, and we need a sysroot. But all this pulls together, and you can see here actually within this quick example taken from the platform when we've installed it for the 104, you can see the clock frequencies, you can see the CPU clock frequency, but you can also see all the other clock frequencies that are available within there. And you can see, and we'll look at this in more detail coming up, but you'll see also the XR, you can see the Xilinx runtime, and you can see the domain names there. So the platform is really fundamental to Vitis, and it allows us to start building on it. And it's actually, you know, while we're down, Xilinx are really great, you know, the partners are really great in providing these acceleration platforms. But if you've got custom hardware and you want to create your own platform, then we can do that. That's really quite simple to do to create your own platform. And if you take a look at my website, you'll see a couple of examples of how to do it as well. Now, when we run this, we're going to get a few interesting things that you might not be too familiar with. So you're going to see elements such as, we're going to get a compiled binary. Now, that compiled binary is what's going to run on our host. So it's in our cloud instance, our Alveo instance, that's going to run on our x86, in our MPSoC instance, our Zinc instance, that's going to run on our ARM cores. And you're also going to see a new file, a file that you might not have seen before, called an XCL bin. And that's essentially the FPGA. That's the Xilinx binary. That's the FPGA binary, and that's what goes into the programmable logic and runs it through. Now, depending upon which system we're targeting, a cloud system or an embedded system, we get a slightly different output. If we're going for an embedded system, then we get all the boot files, of course, we get all the individual files, but we will also create a SD card, so you can just flash it onto an SD card, plug it into your Ultra 96 or 104, and get going with that, and just turn it on and away go. With the cloud, obviously the hardware is actually, rarely is it sat on a machine like next to you like it is in my office. Normally it's in a cloud, in a data server somewhere, or a cloud office, and then you just have the binary and the XCL bin to access and download it that way. So I want to touch a little bit on our development flow, and it's really a really optimal development flow that we have when we work with Vitis, and we go through 3 different elements. We go through 3 distinct elements of it. We're going to go through, first off, we're going to create our source code, and we're going to take a look in a little while about what's involved in creating that source code. But our development flow methodology is we're going to create our source code. Once we've created our source code, we're going to do what's called software emulation. Now, software emulation is just we're going to use the QEMU emulator. We're not going to do any acceleration. Even if we want to have acceleration later on, we're not going to do any acceleration. We're just going to use the QEMU, the software compilers. And what we're going to do is we're using that very quickly to find syntax errors, because, hey, I always seem to put syntax errors in my code. And we're going to do the algorithm verification as well, so as we can prove that the algorithm is working how we want it to work. Before we move on and take any more time to progress it, we want to make sure that our structure, our algorithm, is pretty much what we intend it to be. Once we're happy with that, we can move on to the hardware emulation. Now, hardware emulation, we're going to call some of the HLS, the high-level synthesis that sits underneath Vitis, and we're going to create the actual acceleration kernels from C or C++ or from OpenCL C. And what we're going to do then, using the hardware emulation, is we're going to go around, and we're going to have some great slides in a few minutes' time about the eternal battle between when you're trying to implement things with high-level synthesis between performance and resources. But that's what we're going to do in our hardware emulation. We're going to look at our initial code, which has been written, and we're going to run through that and try and work out how to optimize it to really take the best advantage of the programmable logic that's there. That, you know, this truly parallel logic, we want to take the best advantage of it, and it's likely that we've written our software with our sequential software world head on. So we're going to take a little bit of advantage to do that, and we're going to look at how we can optimize the performance, the interfacing, and get that trade-off between the balance of the resources and performance, and get it all in there. Once we're happy that we get all this right and ready, we can click on build, and the project will go through and it will build the bit stream. Now, today, in the interest of time, you know, the software emulation and hardware emulation, I'm going to show you live as we go through it. Hopefully, the fact that I'm hosting a webinar won't slow it down too much, but the examples we've got will take maybe a couple of minutes to run through, so it's a great time for people to ask questions. But when you click the hardware build, the final build files, it's going to go away and it's going to create the design. It's going to do the synthesis, the place and route, and that's going to take a little bit of time. So today, the only time I'm going to do that, or show you how to do that, is when we've got the final element of Lab 2, which is when we implement the DPU, because otherwise you're just going to sit watching my computer build hardware, and we can all see that on our computer. And the important bit is understanding this software and hardware emulation flow. So now we've really introduced Vitis and the structure and the elements of it. One of the key things I'd like to talk about, actually, and I've mentioned it a few times, is the OpenCL framework and what exactly it is. And it's really quite exciting, because it's an open standard, and it's an industry standard for parallel computing of heterogeneous systems. So, you know, a heterogeneous system is any system that's got different processing elements in it. So it could be something as simple where you've got the Zinc MPS SoC processing system itself is a heterogeneous system because it's got the A53 and the R5 processors. It's even more of a heterogeneous processing system because it's also got the programmable logic in there. And this is what OpenCL is designed. So OpenCL is designed in mind that you can write code to leverage, to create high performance accelerators that are portable across a range of different acceleration technologies. So they could be portable across CPU, GPU, FPGA, and DSP. And to move that code from one target to the other, you don't actually change anything. You just move from, you just recompile the code. You don't have to change the code. You just change how you compile the code. Now, obviously, when you move across there, the portability is guaranteed. What's not guaranteed is the performance. Obviously, as you're moving from different types, the performance will vary. But that's really quite a powerful, function that we get with OpenCL and using OpenCL. And this is really, OpenCL is really the backbone of Xilinx's Vitis offerings. So, and this is why it's seen. This is why OpenCL sees such quite wide market adoption and support. So we've touched on this a little bit already, but the OpenCL framework, it generally works around two elements. It works around a host and an OpenCL device. We might call that OpenCL device an accelerator or a kernel, but it's all roughly the same thing. And the system will only ever really contain one single host, but we might contain several accelerators. So we might have several. We will have one host and several accelerators, which really brings it all together. Now, when we do this, it's quite important to understand how we generate this code and how we generate the solution. So we have the host, and the host code is generated typically right in C, C++, Python, and we make use in our host code. We make use of OpenCL APIs that are available, that are provided with the relevant runtime. So in this case, they're provided with the Xilinx runtime, and we make use of those APIs to manage the life cycle of the design of the tool and pull it all together. Now that's important because that means that our tools, our host C is still fairly independent, and we're working just with the OpenCL. Now the kernels themselves, they're actually written slightly differently if we're using OpenCL, and they're written in the OpenCL C language. Now the OpenCL C language, it's C-like, but it's not quite C. So there are some differences, and that's because of the fact that you want this portability of code. So you want to be able to move from GPU to GPU to DSP to CPU, and they might have roughly the same capabilities, but to programmable logic, again, that's a slightly different capability. So you've got a slightly more structured, slightly more formal language in the OpenCL C language to develop and to create these OpenCL devices, these OpenCL kernels, these accelerators that we're going to put in the programmable logic. Now, when it comes to compiling this, what we've got is we've got several ways that we can compile this. The host obviously is going to compile using a standard compiler. Maybe that's GCC or G++, because it's just pulling into the APIs. If we're using Vitis, we use the XC++. But the kernel is developed using really specific vendor-specific compilers for that particular accelerator. So in this instance with Vitis, we're going to use the V++ compiler to compile the elements for the programmable logic as well. And while I'm talking about this, actually, and we're talking about OpenCL, I just want to touch on a point that somebody's just asked in the questions, which is a really good question actually. So I'm just going to do a little segue and talk about it actually. And somebody asked, what's the difference between OpenCL and OpenAMP? Now that's actually a really good question, because OpenAMP is, for those that don't know, OpenAMP is the Open Asymmetric Multiprocessing, and OpenAMP is very similar to OpenCL in that it's designed to allow heterogeneous computers to communicate, and for one to manage that life cycle of the of other processors transfer data. So OpenCL is really good in that instance. OpenAMP is really good in that instance. But OpenAMP is not really designed to be able to work with what you've put in the programmable logic, those programmable logic accelerators, those devices that we're going to be creating and leveraging in the programmable logic. So OpenCL and actually OpenAMP actually sit in the Zinc MPS SoC ecosystem. They sit really nicely together because you can use the OpenCL to communicate with the programmable logic and benefit from the acceleration there. You can use OpenAMP to manage the communications, the lifecycle modeling between the A53 and the R5s. So I think that's a really nice nice system that pulls it all together and pulls it all through there. So we have our execution model is really quite exciting, and we have a command queue model that we use with our OpenCL devices. Now these are created by the host, and it's attached to a single device. So we create the command queue and we attach this to a host, and then we run through the commands that we want to send to that host. And there are basically three types of commands at a high level. If we look at the high level, there are basically three types of commands that go down the command queue, and they are kernel execution commands. So they're the commands such as execute this kernel now, and I'm going to go back and they are other commands are such as memory commands where you want to transfer data prior to executing the kernel, actually. So prior to executing the kernel, you're going to want to transfer data across into the kernel memory space such that it's got the data that you're asking it to process. And at the end of it, you're going to want to pull that data back out so as you can get your results out of it. And of course, you've got the synchronization commands that go in there to synchronize the system and make the system all synchronized up. Now we have quite an interesting memory model when we come to this and when we talk about this. We have quite a really interesting memory model in this application. So we have basically three types of memory objects. Excuse me. We have the buffer objects, and they're contiguous blocks of memory, and they're available to these acceleration devices, acceleration kernels that are available to run to the kernel, and they're accessed there. We have image objects, which hold just sort of images only, so they're really storing and formatting large areas. And then we have pipes of data, which are organized as FIFOs and can be accessed as read-write and such like as well. It gets a little bit more complex than that, because we actually have 5 subregions of memory objects. So we have the host memory, which is available only to the host. So the host memory can see this, but only the host. We have global memory and global constant memory, which is available to both the host and the device, and to the acceleration kernel. And that's what we can see. That's what we can see there. And we can use this to communicate, to transfer data to and from the accelerators and the kernels. We also have local memory, so that's local to work groups and can be shared by elements in a work group. And then of course we've got the most private element of all, the private memory. So we have this really interesting memory structure that we need to work around and work through as well. Now, one of the key things with all of this OpenCL development actually is optimization, and we're going to take a look through the labs that as they come up. The next we have the lab 1 and the lab 2 as they come up, and we'll walk through that. But we have some optimizations that we need to run through and be able to do that. And to do this, we need to be able to optimize at both the host and the kernel and the accelerator level. So we can pull that through. We can get the best possible performance of our system by actually optimizing both the host and the kernel, and that'll give us the most responsive solution. It will give us the best solution that we can then deploy to our customers. One thing I should say actually is when we develop kernels, it's possible to develop them using OpenCL, or we can use C or C++. When we do that, the optimizations that I'm about to talk about, the syntax changes slightly between whether you use C, C++, or whether you use OpenCL. I've put a little table at the back end to actually show you this comparison anyway, so as you can run through it. But let's take a start really at the host optimization. And what you'll see as we move into this host optimization, as we move into labs coming up into the lab 1 and lab 2, particularly lab 1, when we take a look at lab 1, you'll see some of the elements, some of the tools that are built into Vitis to allow us to do this optimization, because we don't want to do it by hand and have to think about it. We want the tool to really guide us and to help us. And that's really what Vitis is going to do. It's really going to give us that guidance, that help, and that assistance to allow us to focus in, to narrow in on what areas we want. So some of the things we can do with the host optimization is we can really be quite efficient and really focus upon that data movement, because the data movement between the process system and the programmable logic, we want to move as much data as possible, large chunks of data, not small chunks of data, but we want to be able to make that in an optimal way as possible. And we might also want to look at how we compute the scheduling that we run in our command queues. So normally we might want to run through the optimization of what we think about with our PCIe link or our DDR bank and on-chip memories. And then we might want to run the software emulation that I was talking about. And that software emulation will allow us to verify the functional correctness of the design. Once we've done that, we can run our hardware emulation. And from that, we can look at the analysis. And I'm going to show you how you can look at the analysis tools in Vitis in Lab 1. We're going to pull that out. We're going to take a look at it. And you can look at how we can analyze the kernel compilation, what reports we've got. We can look at the timeline, the traces, the devices, the hardware transactions, and we can use that information to really narrow in on that aspect of is the overall performance goal met? If not, then we can, if it is, we can sort of build it and run it on the accelerator card, the application card. If not, we can iterate around it. But once we actually get it into the real system, we get some hardware in there, we can also analyze and profile the system, and we can iterate around again to try and get that optimal data movement. And that really is quite key. That moving data on and off the accelerator is something that you should focus on quite quickly. Somebody's asking if I can comment on this, comment on how we can do this and how we can. And I'm going to talk about that in a couple of slides' time, as to how we can run through all this. Of course, the other thing we can do is we can look at the optimization of the host queues. So we can have multiple in-order queues, or we can have single out-of-order queues, and we can feed them into the scheduler that way. And that will help us really then determine determine how the commands are scheduled and how the commands are run to get the best out of our command queues that we've got going in there. But of course, actually, the main benefit that we're going to get in our system is from optimization of the kernel, of what we actually put in the program, of what we actually pick up and put in that programmable logic. And that really comes through this kernel optimization here. And that's where we have, there's a lot of options that we can do. And we're going to talk through some of the high-level options that we might want to do, some of the basics that we might want to do to make sure that we get the best performance when we take our device, we pick it up, and we put it in the programmable logic. Now, one of the first things that we want to do is actually, if we're working with C or C++, we want to avoid native data types such as ints, floats, and doubles. And the reason that we want to avoid that is because they're going to synthesize when we go into the hardware as being quite large logical structures. And that might not be the most efficient implementation for what you're trying to implement in your hardware. So it's going to hit you in terms of the utilization, but also in terms of the performance that can be achieved once you're using these. The best performance we can get is to actually use the bit accurate types in the C and the C++ kernels. And we can do that using the arbitrary precision integers or the arbitrary precision fixed point libraries. And they will allow us to work with and we can still work with floating point numbers, and because they really handle that floating point to fixed point conversion for us quite well, so it masks it quite well, and make sure still that all our mathematics is correct when we work through it all, but you're working with a fixed point number. And that really enables the programmable logic to be much faster, much smaller, and a much better implementation than what it might do if you'd used a native C type. Now, one of the other areas as well is also about this interfacing, the kernel interfacing, and you'll see this when we look at Lab 1 in a few minutes. Is you'll see the ability that we have the ability to run through the analyzer and look at the interfaces that exist potentially between the host and the kernel. And really, what we want to do is we want to be transferring big chunks of data, bigger amounts of data as possible. We want to be moving from that process system to the programmable logic, and we want to be leveraging DMA to do that. So DMI, direct memory access, to do that, to pick it up and move it across. And we can do that if we write our code correctly. So if we use pointers in our code, when we define large arrays and we use pointers to access them and work with them, then by default, the Vitis compiler is going to pick these up. It's going to say these are global. This is global memory, and it's going to use the master AXI interfaces to transfer this data across, and it's going to use burst transmissions to transfer that across. If we use scalar type data, then it's going to use an AXI Lite type interface, and that doesn't have a burst interface. That doesn't have burst capabilities. That's a single beat read write access, and that's really going to slow down your functionality and move it through there. So now Vitis automatically, when it does its compiling, it's automatically going to select the correct interface type, whether it be a MAXI or an AXI Lite, and it's going to do it like that. But what we can do, the max data width is 512 bits that when we're working with AXI interfaces. So if we want to, we can ask the tool, we can drive the tool to actually use the maximum data width possible so that we can get more data going across there and running across that interface as well. Now, it's not just our interfacing where we win or lose now and be able to get that benefit from the programmable logic. What we find in a lot of instances is that when we write high-level code that's going to be turned into an accelerator via HLS or via Vitis, we tend to write code that use lots of loops and iterates around a number of options several times. And by default, because you don't want the Vitis compiler to just use every little bit of logic element in your device when you click on compile. By default, by default the compiler creates logic structures that only start when the previous iteration of the loop's finished. So it works in a sequential manner, very, very similar to how a software world does. So in this example, you can see it iterates through the 3 instructions. Once those 3 instructions have been iterated around 3 times, then it goes back and you can start a new interaction. So that takes at least 8 clock cycles before you can start your next iteration. But what we can do by pipelining the loop and using the pipeline structure is we can use the pipeline function to actually make it such that while it's doing the first cycle, while the first cycle is being implemented, the next cycle is being executed, and then the next cycle's being implemented. And we can run through all that, and that brings us a shorter number of cycles, which is really, really exciting and gives us that capability. Now, what I should say is whenever we do this, we are trading off performance for resources. So in the first instance, the loop without pipeline, obviously it uses the fewer resources possible. In the example with the loop with pipelining, it uses more resources, obviously, and that's the important bit that we need to get there to. But there's another thing that we can do with loops as well, and we can not just pipeline them, but we could actually, depending upon the loop structure and the dependency between loops, we could actually unroll that loop in its entirety, and we could see as in this example, all 4 instructions occurring within 1 clock cycle, as opposed to them occurring sequentially one after another. And again, this gives us that capability to get more performance out of our system, but it comes with obviously a slight impact, and it uses more resources. Now, in this example, for 4 clocks, for implementations of this simple addition circuit, it's not going to be an issue. It might be an issue if you're trying to process a HD image processing frame, which is 1920 by 1080 lines. In that case, you might not want to unroll the full loop. You might only want to unroll the loop partially, such that you still get significant benefit of performance, but without actually using up every little resource in the design, because you need to think about, you need to leave other elements of the logic as well available for the system. So if you think about it, both the pipelining and the unrolling, they're actually working at a very coarse level. They're working at a instruction level in our code. So they're looking at it a simple instruction level, and we're doing the pipelining or the enrolling of that. What we might want to do is, well, we might want to do some data flow. So if we've got several functions that are being called, and one after the other, we might want to not wait for the first function to finish before the second function continues, before the third function continues after that. What we might want to do is we might want to run them through in a pipelined area. So we might want to do some task level pipelining, which is what the data flow pragma allows, and that's really quite a powerful thing. There are some issues. There are some complexities around it. Obviously, you can only have a single producer and consumer. You can't bypass tasks and you can't have feedback between tasks or conditional execution because it can't necessarily do that nice data flow pipelining in that case. But it is, the data flow pipelining is a really good example of where you can get significant benefits actually just by looking at the flow of the functions that are going across. Now, one of the things that we also have, so we've looked at loops, and if you think about it, a lot in our designs, we're going to actually use BRAM. So we're going to use BRAM in the programmable logic to store data, and it's going to be there to store read-write data, to store results, or anything like that. And BRAMs are actually, they're very limited in space because they're very limited in bandwidth, because you've only got essentially 2 read and write ports, so you can't access all the elements of BRAM at any one point in time. You can literally only go through the interface ports that are there. So what we can do is we can run through some optimizations, and there are 2 real optimizations that help us when we want to fracture that BRAM and make it a little bit more, give us that high performance bandwidth. And we can do this by using the partition element, which will separate the block RAM. So if we've got 8 elements stored in a block RAM memory that we want to access, if we partition it, that will separate it all into 8 separate block RAM or 8 separate registers, such that they can all be read in parallel. If we do a reshape, then that allows us to reshape the structure of the words that are stored in that BRAM and the size of the words that are stored in that BRAM. So we can actually get a much more efficient reading and writing of the BRAM without having to necessarily do the complete partition. So these are really quite powerful functions that we need to use in our design and get it through and get it working. So as I said actually at the beginning, you know, there's a couple of differences whether we're using a C++ kernel or whether we're using a OpenCL, and as to the attributes that we want to use and pull through. But you can see those there. And if you need any further information, then please click on this Vitis link as well down the bottom. That'll take you to the latest documentation where you can read up on all these optimizations, and it'll give you a lot more information. I've just given you kind of a quick, we're working through this lab type issue information. That will give you a lot more detailed information so as you can get through it. So this is where we're going to start in a minute. We're going to fire up the GUI, and we're going to start working with the live example. So if you've not got the lab book and you want to follow along, then get the lab book. This is going to be our environment that we're working in. So this is the GUI environment. We've got the project settings, and we're going to do a lot of our control through this project, through these project settings and the assistant down here, which is going to be really, really quite powerful. We can also, I have that slide in there twice, but we also use this to set the emulation flow or the flow that we want to work with, or whether we want to see the hardware or not. And then finally, I want to touch a little bit, just before we go away and do it, I want to touch a little bit on the debug capabilities. So we have the GDB debugger and the debug server, and we can run this host code and this kernel code, and we can do this debugging in QEMU using our hardware and software emulation. We can also, as I'm about to show you in the lab, we can also use transaction level modeling actually and open up Vivado when we do hardware emulation, and we can see the waveforms that are going off. We can see the AXI transactions, the AXI waveforms. That's really quite exciting and quite cool to well, it is to me anyway. And then we have the ability to do all this. In the hardware flow, we can insert ILAs if we want to, such that on our real world hardware, we can see this and have the ILAs in there and run through the design in that way and capture the data on the hardware to try and find out if we have issues in that. And then otherwise, we can just debug as normal using the QEMU and the logic simulator, which is what we are about to see now. So now we're going to take a look through two labs. We should have got about enough time to run through it. It took me a little longer to get through the slides than I was thinking. But what we're going to do now is I'm going to just share my screen. So hopefully enable screen sharing, screen 1, and share. So hopefully now you can all see my desktop. And what we're going to do is, if you've got the labs in, if you've downloaded the lab book and you've got Vitis installed, what we're going to do is we're going to step through these labs, and hopefully I've run through it 3 or 4 times this morning and it all worked fine. But obviously with live demos, things can go a little off there. So what we're going to do is we're going to open, the first off thing we're going to do is we're going to open a browser, and then we're going to start the we're going to start the Vitis tool. Now, how we do that is we're going to go to other locations and computer. And if you followed my instructions, then your Vitis will be installed under Tools, Xilinx, Vitis 2020.1. And what we would need to do here is that if this is the first time we've run it, we're just going to run this setup script. So we're going to open a terminal. And we're going to type a couple of things in this terminal. The first thing we're going to type actually is we're going to set up a library path. Before we launch Vitis, we're going to set up a library path just so that we can make sure that we can do our software emulation correctly. There's a open answer issue. So can anyone see the screen yet? I just saw a comment saying you can't see the screen, only see the slides still. But that should be the stream is maximized. Perfect. So everyone can see it. So that's good. So what we're going to do is we're going to type this in, and we're going to just type in export. And I can never type properly when I'm doing this, so it'll take me a few times here. We're going to type in this export library path, and we're going to set that equal to the USR directory, to the lib, to the x86 underscore 64 dash Linux dash GNU. Oh, not GNU. I think that's correct, but just because I'm doing this live, you don't have to do this. I'm just going to quickly check that I set that properly, and that looks right to me. So what I'm going to do then is we're going to source the settings, and then from that we can actually open our Vitis tool. So I can type in Vitis, and the tool will run through and should open. Now, one of the first things it's going to ask you to do is what's the workspace that you want to save your project in. Now, this was actually my demonstration area earlier on, so I'm going to go back and I'm going to create a new folder, and I'm going to call this Vitis Live USA, because this is the time zone that we're in. And I'm going to select, I'm going to run my browser here, run my Vitis here, and click on OK. And it's going to take a few seconds, and it'll run through, and you will see the tool open. Now, this is a really, really nice tool, really quite simple, really easy to get up and going. And what we're going to do is, I think I have, someone was just asking if I could enlarge it, and I think I have. I've clicked on maximize to maximize this stream, so hopefully it should be done. Let me remove the slides because we're not going to come back to them, so maybe that'll make it a little bit better. And then hopefully everyone can see this platform. So what we're going to click on now, we've got these projects. We're going to click on Create Application Project. And we always get this kind of standard application project, which explains a little bit about it. If you don't want to see it again, you can click the skip, and then anytime you want to see it again, you can just hit the back button on it. But I'm going to leave it as it is for the time being, and I'm going to click on Next. What we'll see here on the next tab is we will see the platforms that you have installed on your system. And in this instance, you'll see I've got 3 platforms installed on this application at the moment. I've got the Ultra 96, I have the ZCU 104, which is what we're going to create the example for, and I have the Alveo U200 as well. So you'll notice here that the flow, both of these are showing that all of these can be, both the embedded platforms are showing that they can be used for the embedded and the accelerated flow if you want. And the data flow one shows it can be used for the Alveo card shows it can be used for the data center. So I'm going to select the ZCU 104 and click on Next. And then I'm going to type in the name of the project. And in this project, I'm going to type in Lab 1. And you'll see that it's automatically setting up a new system project for us here. And a system project is really, it allows us to have a collection of different projects and different accelerators in different domains underneath it. So we're going to associate this with the Cortex A53. We don't have any option. in this instance for this platform, and then we're going to click on next. And now what we have to do is, if you remember when you did that install with me, I asked you to install install and extract a sysroot, a root file system, and a kernel image. So now we're going to go and set these up in this platform. So I know that my sysroot resides under sysroots, and we're going to select the we get this right the right way around. We're going to select the ARM A64 directory there. We're going to select the root file system. We're going to go back up into the directory that we installed it in, and we're going to select this extracted root file system, and we're going to click on OK. And then for the kernel image, we're going to do the same again. We're going to click on the image again. So these are leveraging the Xilinx common platforms that are provided from the Xilinx website, and you can download them from there, which I think is really quite nice, to be honest. We can click on next in that case. And in this case, you'll see some application templates. You may see a few less than this, and this is because I installed a few platforms early on. But the one we want to do actually is the vector edition. So click on the vector edition, and this is the example that we're going to open. And then if we click on finish, it will run through and it will create our application. Now, if this is the first time you've seen Vitis, then you'll see this. We have this application project settings here, and we have our systems tab here. So if we needed to change anything, say if I'd got the sysroot wrong, or I'd used the wrong root file system or the kernel image, or I wanted to change the packaging applications, then this is where I would make these changes. If I wanted to change the platform, I could change the platform. But the real interesting element, the real area that we're going to be working with, is this element here in the middle where we've got the application settings. You can see we've got options for doing kernel debugging, for reporting level, for hardware optimization, and for the software emulation, or setting the software emulation or the hardware emulation. What we're going to do now actually is we're just going to take a quick look at the source code, so as you can see this source code for the first time and see what we're actually working with. You can find the source code under the source directory, and we're going to start by opening the VAD CPP. And what you'll find here is this is a standard C file, C++ file actually, and you'll see that we've got the pulled through all the elements that are needed. So it's got the main element there. You can see we're pulling in the name of the Xilinx XCL bin as argument 1 from the command line when this is first called in the application, and then you can see we're doing the information that we need to get all the platform information that we're running on from the Xilinx runtime. So it's running through, it's grabbing all that platform information. If the platform's not correct, obviously it's not going anywhere. But if it is correct, then it's allowing us to move forwards, and it's allowing us to download the application. So here where you can see we're creating the context for the device, and we're creating a command queue, and then we're loading the XL bin into the programmable logic. So this is what the application's doing. It's running through, it's setting up the kernel, it's setting up some buffers to transfer the data to be read to be supplied to the kernel, and reading back the results as well. It's setting up the initial values, and then it's moving this data across these buffers. Finally, actually down the bottom here, it's actually running the kernel and doing the processing and getting the results back. So that's really quite a simple, really quite an example, but it's a very elegant example that really gives a good understanding of what's going on when we work with Vitis and the OpenCL environment. So it's really quite good. What we're going to do, we're just going to click on close of that, and we're going to open the kernel VAD CPP. So this is actually what's going to get accelerated into our programmable logic when we click on build. But what you'll see down here is we have some buffer sizes defined, and we're just using a standard C kernel here. So we've defined a C kernel. We've got our inputs, so our 2 inputs, and we've defined these as pointers. So if you remember, if we use pointers, then we get the then we use the master AXI, the DMI type interfaces, the high bandwidth interfaces. And if we use scalars, then we don't. So you can see that we've got a scalar being written in there to set the size of the application that we're doing. So we're looking at these. So we've got these three high bandwidth interfaces and a low speed bandwidth here. We've also got some of the pragmas that we were talking about instantiated in the code, and these are just basic pragmas actually in this one, just to tell the tool and inform the tool how many times, how many iterations around the loop it's actually going. So this is a really nice simple application, and just to give us everything that we want to understand and to be able to drive the tool. Because what I'm trying to teach you now is how to drive the tool such that you feel confident in yourselves to go away and create your own application. So if we open the viad.h, you'll see this is a fairly standard header file with a template definition in there for the structure. So that's all nice and simple, all really good. But what we want to do is we want to work out how we can actually then take advantage of it and start working with it and debugging it. And if you remember, the first element I said, the first challenge I said, was we want to make sure that we've got the software right and the algorithms right, and that's where we're going to come through and we're going to use this. So we're going to use the emulation, so we can run the emulation software. So I'm not going to change anything. You can see we've got emulation software ticked here, we've got emulation software ticked here. What I'm going to do is I'm going to come over here and I'm just going to click build here, and that's just going to build me the application in the set for the software emulation. So this will just be, let me just try moving this screen across to the bottom there. This will just be like it's running a normal software application. It's building it to run it on the processors. Actually, we're going to run this on QEMU. So it'll take a few, maybe 2-3 seconds to run through, maybe a little longer because I'm doing a screen sharing session, and it tends to take a little bit longer when you do that. But hopefully not, because this is quite a beastie Vivado machine. So you'll see it run through, you'll see it compile, and hopefully you'll see it pop out in a second or two with a nice compilation showing that the build is complete. Or did I miss that? No, it's just running through and packaging it now. You can see it running through. You can see the assistant under here, and this is the assistant under here is what we're going to use in a minute to launch our application and to get that all running. So it took a little longer than I think normally. I think it took about 5 or 10 seconds earlier on this afternoon, but that's to be expected when it's sharing resources with everything else in the in the environment. So what we're going to do now is we're going to launch the debugger and take a quick look at the debugging capabilities. We're not going to run it all the way through to the end of the application. We're just going to take a quick look at the debugging capabilities. And how we're going to do this is we're going to click on this emulation software here, and we're going to click on this option down here that says debug, and we're going to click launch on emulator. And what this will do after a few seconds is you'll see it will pop up and it will ask us if we want to start running the emulator. So what we're going to do is we're going to click yes, of course we want to start the emulator and start debugging, and then we're just going to wait for the emulator to start. Hopefully it'll start very quickly, and you can see down in the bottom, you can see down here, you can see that QEMU is actually booting. So you can see this is running up. So here it's actually loading QEMU is emulating being the ARM A53 processors. So it's loading the pedal Linux image onto itself. It's loading it up, and then it's going to allow us to run our application connected to QEMU, and it thinks that it's actually within the we're running as it's same as it is we're running in the A53s. So it allows us to do that debugging, that register set, that break pointing, that watching registers, and all the things that we need to do to get through that initial software development stage of, is our software good? Do we have any syntax errors? Obviously we don't, because it compiled, but now we're more focused on, is the algorithm correct that we want to do? Is that correct? Obviously, because we're using an example from Xilinx, we know it's perfectly correct, so we don't need to go running through and look for it. What we want to do then is we just want to see how the design loads. So if you take a quick look, once the design's loaded into the emulator, what you'll see is the debug perspective will open. and that debug perspective will open. The software will actually pause. So the application, the software, the executable that we've created is being downloaded into the QEMU environment, and we can see that down here. If we maximize this, we can see our QEMU environment down there, and we've actually paused the application at the start. Now, if we hover a mouse over it, we can see the values, and we have the values and the watch table up here. Now, what we're going to do in this example, we're going to do a very simple element. We can use these buttons up here to actually, so we can just run the target to the end if we want. We can terminate and disconnect the system, or we can, if we want to, we can just single step through the application. So if we take the option of stepping over, we will see that as we step over, we step through the device, and you can see things are changing, and you can see things are being updated here. So for instance, you can see the file name of the binary container in this example is showing as binary container _1.xcl bin, which is really important. You can see the size of it in bytes. So that's the name of the programmable logic accelerator that we want to load into our design. Obviously, we don't have one at the moment because we've not compiled it. Now, what other things we can do? So we can click on this. We can double click in the edge here, and that's what I'm going to do on line 78. If we want to insert a breakpoint, we can double click on the edge, and then we can click run the application, and it will resume running right up until the point that breakpoint is hit. So this gives us the ability to do our normal traditional software development and software debugging as we're working through this life cycle. Now, what I actually want to do now is I actually want to move across. Now I've shown you that we can load the example using QEMU. I actually want to show you something and the basic breakpoints and step over, just the introduction of Eclipse like we've seen previously. What I want to do now is actually show you the hardware emulation, because that's where it really begins to get interesting. So what we're going to do is we're just going to click stop here, and we're just going to terminate the Linux debugger. I'm going to just see that I have the emulator. I'm going to stop the emulator, which will stop in a second or two, I promise. You can see it's all shut down. I'm going to close that now, and I'm going to click on this button here to go back to my design environment. And now I'm happy. So I'm playing along with the role of a design engineer. I'm happy my design works, my algorithm works, my simulation, there's no syntax errors. But what I want to do now is start focusing on the programmable logic elements, the design elements that come through in when we move that into Accelerator, and leveraging those pragmas we were just talking about, where we go through and we take it to creating the implementation. So what we're going to do now actually is we're going to change this element here from software element to emulation hardware. We're going to change the reporting level here to reporting level 2 for debugging. You'll notice that the hardware's changed to hardware emulation. And what I'm going to do then is I am going to click build. And now this time, I'm really not sure how long it's going to take. It should take maybe a couple of seconds to run through and to pull this all through together, and that should. And what you can see now is it begins to create the target. So you can see it's actually compiling device. It's creating the kernel, the add, and it's going to allow us, once we've done this, we're then going to be able to take a look through our design and take a look at what elements of that design are performing well, what elements aren't performing well, and how we can understand it a little bit better. So this will take, because this is called in Vitis HLS under the hood, this will take a few more minutes, but it's still, this iteration process is still a lot faster than it would be if we were working with doing the place and route, doing the synthesis and the place and route, as we would be doing when we're doing a full hardware implementation. So we'll give it a minute or two while it runs through. Hopefully it'll not take too long. Like I say, at the end, I'm going to finally build the DPU in there, but actually I'm going to do a little bit of a Blue Peter trick and switch you out to one I did earlier, one I built this afternoon, because it takes about 40 minutes to build, and we won't have that time in this webinar to do it. So you can see that's running through. It's running through. It's creating the block diagram now. It's created the virtual. It's created the kernel. It's creating the block diagram in Vivado for us now, and it's moving through that step to be able to create as a more accurate emulation target. So while we do that, I'm just going to take a quick look in the chat and the questions and see what people are saying. So a few people have asked actually if this webinar is going to be available offline. And yes, obviously that we'll make this recording available to you all that registered, so as you can come along and you can see that webinar, and you can watch it in your own time. You can rerun it as we work through this. So it shouldn't be too big. So the emulator, we're going to run through the emulator. Somebody's just asking a question about they missed how to run the emulator once built. On the software side of things, you can just literally right click in this one on the software emulation, and then go to debug and launch on emulator, and that will launch it on emulator for your software if it's not debugged. I appreciate if you are following along with me. Obviously, our machines are all implementing doing the builds at different rates and different speeds. So it will be slightly different as we're running through that. But hopefully it's giving you a good introduction and a good example of how to do it all. So now we can see it's making a little bit more progress. It's running through, and it's going to begin to create the software now. So this would be pull it all together. Another couple of minutes, and we should have a design that we can begin to look at in our external in our analysis views and take it through. So there we go. It's just created the SD card example for us. So someone was just asking, is there a good resources to learn all about this? And obviously the Xilinx website is really quite good. You know, obviously Xilinx provide a lot of examples. There's the Xilinx developer website, and there is also, I'm going to plug myself, you know, there is also my own website, Aduvio's website, and for the last 7 years now or so, I've been writing a weekly blog on how to use Xilinx FPGAs and how to leverage Xilinx FPGA technology. And you know, Vitis features pretty significantly in that, and there's a lot of hacks to projects I've created that give you full examples and everything. So we can see that now. We can see our builds finished now, and we've got a hardware emulation design that we're ready to go and take a look at. So let's take a look now at what we can do with it and run it through and see. Let's run through the hardware emulation and see what it looks like when we run through to the end, and then let's go back and pull this back and take a little bit of a look at some of the things that we can do to run through this. So what I'm going to do now is I'm going to click on this hardware emulation, not software emulation, hardware emulation this time. And I'm going to right click, and again, I'm going to do debug, and I'm going to do this launch on emulator again. Now I'm going to click on launch on emulator. And this is going to ask me again to start the emulator and debug. So I'm going to click yes, because obviously I want to do that. Now this time it's slightly different, because by default, the emulator is going to begin to start up, but we're going to see something else happen in a minute or two. Hopefully we are anyway. So what we're seeing is Vivado is actually opening as well. And you can see this as running through as Vivado's opening. You can see that it's starting up with the simulation, the waveforms that we might want to see. And if we flick back to Vitis, you'll see a warning in Vitis saying, please click run all in the Vivado simulator. So this is what we're going to do. We're going to click run all and then click OK here. And what you'll see now we've clicked run all is the transaction level modeling will be enabled to connect to our QEMU emulator. And then our QEMU emulator is going to boot up and allow us to do this. So what we're going to see here, and this is really quite cool. If you're a geek anyway, it's really quite cool and exciting. But what you're going to see here is you're going to see executing the code on QEMU, but actually you're going to see the hardware being simulated in Vivado, and you're going to see waveforms in Vivado, and you can do breakpointing and such to help you develop our system. So once this is started, we'll run the application, and then we'll see where we end up at the end of that. It'll just take a few minutes for it to load up and run through. So Bill, actually, Someone has just asked if a Zybo board would have enough resources to experiment with Vitis. So I've not done the 7010 version, and I've not done a Vitis, a Zybo board actually, but I've certainly done Vitis examples on the Zinc, on the MPS, on the MicroZ, which uses the 7020. I can't remember if I've done the 7010, but yeah, there is enough logic there that you can begin to experiment and try and see this example, see these examples and see the benefits of working on the working with Vitis and this acceleration, this OpenCL flow. So what you'll see this time actually we see it stopping again at the design entry, at the entry point again. So what we're going to click now is we're going to click on resume, and then we're going to keep an eye on this terminal down here and our QEMU emulators down here. And if we pull this up slightly, hopefully what we'll see is we should have seen something running. Let's see anything running. Oh, that's a little odd. We should have seen, oh, because it's stuck at the breakpoint there. So I'll click run again. The beauty of live demonstrations. So you'll see the binary container being loaded. You'll see the binary container being loaded there. You'll see the result come back that says test passed. If we actually maximize the emulation console, you'll see what's going off in fully and what you'd see on your Vitis terminal if you were connected to this over a terminal. So you'll see it loading. You'll see it loading the Excel overlay. You'll see it coming back. You'll see it doing the tests, and you'll see it reporting back. So really quite a nice flow. And if we go to Vivado, and I'm just going to click pause on this just to stop it doing, what you'll see here as well is you'll see this waveform information here. And if you zoom in, and you can zoom in, you can see what's going off at a system level with reads and writes and data transfer. And you can see here the number of stalls that are going off as well. So that's really quite a powerful, gives us some good debugging information that's going off there, and allows us to work on and optimize our system a little bit more than perhaps what we have been doing. But now we might want to look a little bit more at a few of the other options that we have in our design to do that optimization and to be able to work out where to do the optimization in our kernel that we want to pull through. So just for the time being, I'm just going to close. I'm not going to come back. We're not going to be coming back to this. So I'm just going to close Vivado just to free up a bit of memory in my system, and I'm just going to terminate the debugger and go back to the design view. Now, what I mentioned when I was talking about the slides earlier on, when we were working through the slides, was how to actually look at this and how do we optimize it. And I mentioned that Vitis actually has an analysis tool built within it that can allow us to take a look and execute that. So let's take a look at how we can do that. So if we select this XCL, this binary container here, under the hardware element, and if we right click, we get this wonderful option called Open in Vitis Analyser. So let's click on Open. Now this will take a few seconds to run through and open up. But what we'll see when we see this is it will pull through the nice Vitis Analyser that we can use to look at our design, and it will tell us, it will give us all the information that we want. So it will tell us about about any violations, any guidance violations that we might have, any elements that we could use to get better performance, any areas that we're breaking it. Say if we have imperfect loops or such like. We can see what platform we're working on. We can see the kernel, and we can see all the command line information. What's really quite exciting though is we can click on here, the system design, and we can see our system design of how it actually decided when it did the hardware emulation, how it actually decided to interconnect it together. And you can see here we've got the Zinc processing system here. We've got the high performance 0 interconnect going there, and that's connected to the in 1, in 2, and out. And you can see obviously the estimated resources here. So you can see of this ZCU 104 board, we're using really nearly 0 of the resources, but it's a great example. Now, this is interesting because looking at this system diagram, this system connectivity diagram, we might actually want to try and drive the tool to use different interfaces to connect these, such that the interfaces are all transferring data in parallel to give us a better flow, and like I said, to give us that optimization that we might talk about of that performance, of that interfacing, of that data, of that kernel interfacing. So that's really quite important. We can take a look at the platform, and this platform really just defines what is available to us as the platform. So you can see there's actually 6 interfaces available to us, and we've used a high performance, and it's used a high performance 0. So there is certainly options there to allow us to work with it and to be flexible and to manipulate it and move it through from one to the other. We can see our system elements, so we can see our system estimate. So under the system estimate, we can see what the Vitis HLS tool thinks how it's going to perform, the number of cycles, and the performance in terms of the clock frequency that we've given it, which was a target of 150 megahertz we've asked this to run at. Now, we don't have any on here, we don't have any system guidance on this application, but if we did, we would be able to see the list of system guidance here. And then finally, we can see the report logs and such like that are generated by the tool. So this gives us a real great ability to take a look through and understand and help us optimize this tool. If we want to, we can also take a look at the kernel, so the VAD kernel, and we can take a look through at the guidance, at the HLS information, the HLS reports and loops, and then any logs that might come out of it there. So this begins to give us an idea of how we can understand our design, how we can work with our design to actually go through and optimize it to give us that best performance, to be able to leverage that truly parallel architecture. But there's one other thing we can do as well, and I'm just going to click on close this. There's one other thing we can do, which is also quite exciting and quite interesting when it comes to optimizing this structure. So what I'm going to do is I'm going to click on the kernel itself here. So I'm going to click on the kernel itself. I'm going to right click on the kernel, and I'm going to click on Open HLS Project. So when I click on Open HLS Project, I'm going to get this warning to say be very careful about what we change. Any changes that we make, obviously, we'll have to do the recompilation. But we can click on OK. And this will open the Vitis HLS tool. So this is the tool that gets called underneath the hood by Vitis to actually take our C, C++, OpenCL, and create those hardware gates, those OpenCL, those gates for us. And this will pull through, and it will show you all the information. It will show you all the information about the loops, the scheduling. But what's really interesting as well is we have this analysis view within our tool. So if we click on the analysis side, we can open up the loop. So for instance, we know our loop here has this Vitis loop 76, and we can see that that's taking, if I zoom out a little bit, if I can find the options to zoom out a little bit, we can see that takes a large number of clock cycles to complete because it's running through. So we can see this loop, we can see all the elements of our code. So if we want to, we can, let me just expand that again. We can click on that, we can click on an element in here. Let's click on this next line, and it will cross probe to the source code. So we can see where this element of code, what impact they're having on the design, what it's mapping to, and how this all pulls together. We can also have this rather nice little focus element up here. And now this is interesting if you get a timing violation. So if you get a timing violation, you can put the focus on the timing violation, and it will show you exactly what where the timing violation is, and it's colored in red. So if you want to, you can click on these elements, and it will show you the elements of your code where you might be having issues. And lo and behold, this is what's hitting the timing issues, is doing the reading and writing from the block RAMs and our buffers. So we could do some manipulation and some work in that area as well. If you want to, you can go back to the synthesis area. You can open up source code. So we can open up the source code. And if we want to, we can add in elements under this directory. So we can add in elements of the, so you can see all the optional, the pragmas that are inserted. So if we wanted to insert a pragma, say, on this V1 buffer, we can select this V1 buffer here. We can double click on it. We can tell it that if we make any changes to it, we really want this, the pragma to be written in the source file, not in a directive file. But then we can make any changes that we want, such as array shaping, array partitioning, and save that. And if we wanted to, we could run this through a few times in the Vivado HLS tool, in the Vitis HLS tool, just to see what the implementation is and what effects it is having, and how our optimizations are working on the design. I'm not going to make any changes now because I'm literally trying to show you how to drive the tool, as opposed to and all the capabilities of it, as opposed to doing a real in-depth step-by-step sort of example. So what we've got here, I'm going to click this and close this, and I'm going to go back then to our project, our Vitis project. And if we'd made any changes to the obviously if we'd made any changes to the underlying hardware in the Vitis HLS, we'd have to click on rebuild and rebuild the application, which would take some time. But that really brings us, actually now it brings us to the end of lab 1. And what we've done in lab 1 is we've kind of stepped through how to open Vitis, how to create a project, how to do the software emulation, so as we can check that our syntax is correct, and we can breakpoint and debug and use QEMU, so as we can check that our application and our function and our algorithm is working correct. We've taken a look at the hardware emulation, and we've taken a look at how we can build hardware emulation, the tools available to us to do some debugging, so looking at the waveforms, looking at the Vitis Analyser, looking at the Vivado Vitis HLS, and how we can how we can use those to help us to get better code, better optimized code, better performance within our actual application. And I think that's really important, because we now know at least how we can go through and step by step and create the example. But now, for the last sort of half an hour or so, what I want to show you is AI. Obviously is a hot topic at this point in time, and Vitis AI, we've already talked about it. What I want to show you is how we can go through and create a Xilinx deep learning processor and implement that using Vitis in our flow here today. And it's really simple to do. And once we've done that, the files that we get out at the end, the hardware handoff file, we can use then in our Vitis AI flow with our Cafe and our PyTorch and everything else, and we can pull through all this. So it's really quite a powerful flow. So what I'm going to do is I'm just going to close all the windows here, just so as we don't get too confused. So everything's nicely minimized now in my lab 1 system. And I'm going to go away and I'm going to create a new project. I'm going to create a new application project, and this time I'm going to select the 104 board as well, because I want to put it in the same 104. But I'm going to give it a name, so I'm going to call it DP. I'll call it DPU. Click on next again, and I'm going to set up the sys root again. The sys root. I'm going to set the sys root. Set the root file system. I'm going to set the kernel image. Sometimes I feel like I could do this in my sleep. I've done it so many times the last few days. So I'm going to create this this root file image, this system, and such like on there. And then once this is ready, actually this time around, we're going to create an empty application. So we don't want anything in our application. So we're going to click on empty, and we're going to click on finish. And it's going to run through, and it's going to create as an empty application, which is perfect, exactly everything that we want. Once we've done this, what we're going to do is we're going to minimize. We're going to minimize this. We're going to minimize this. We're going to go back to my home directory, and I've done this half a dozen times today, and we're going to do it again now. So what we're going to do is we're going to create a new folder in folder in an area that we want to work in. So I'm just going to do this in my home directory. I'm going to call this Vitis DPU USA for the USA session that we're doing, and I'm going to click on create. So that's going to create me a new folder. I'm going to double click enter that folder, and then I'm going to open a new terminal terminal window. Now, the thing that I haven't put in the instructions, actually, so I will update, and I realized this just this afternoon when I do this. The first thing we need to do, actually, is we just need to issue a quick command in the window to actually so that it's aware of where Vivado lives. So what we want to do is we want to source, and we want to go to the ops directory, and then we want to go to Xilinx. No, we don't want to go to ops, we want to go to tools. We want to go to Xilinx, we want to go to Vivado. We want to go to 2020.1. I think that's it. Yep, don't want to do that. So I'm going to go to 2020.1, and then we're going to go to settings 64.sh. And we're just going to run that script just so as we're aware of the Vivado tool settings and everything in our tool. And then what we're going to do is we're going to clone the Vitis AI tools. So this is really quite simple. We're going to get them from the Xilinx GitHub. So we're going to type in git clone github.com/Xilinx/Vitis-AI.git. Hopefully that looks correct. I'm going to hit enter. And what it's going to do is going to go away and it's going to clone the Vitis AI for us. Now this might take a minute or two. Hopefully it's not going to take too long. But this is going to give us everything we need to get started and get working with Vitis AI. I'm going to leave you at the end point today where we've got the DPU implemented, and then you can go away and you can experiment more with the Vitis AI and using what you've created to pull that into your design. It looks like it's going to take a few minutes, so we'll take a look, and we'll take a look at the chat, and we'll take a look at the questions. So someone was asking if the Gen CZU platform is available for Vitis 2020.1. I think I did a Vitis 2019.1 platform for the Gen CZU, but I've not seen a 2020.1 platform available yet. I don't know if Digilant have one or not. Somebody's asked a really good question. Is it possible to add accelerator kernel to an existing programmable logic design? And yes, it is. That's the entire point and one of the elements about the great aspects of this Vitis platform. So you could create your design. Maybe you've got an image processing pipeline, maybe you've got a radar image sensing pipeline or something, but you can create this pipeline in your design using Xilinx IP. You can then create a Vitis platform that uses all this, that has all that infrastructure included. So maybe a MIPI imaging pipeline that goes into the processing system, and you can use that and you can compile that platform as a Vitis platform. And then when you recreate your platform, when you rerun Vitis, and if you were to open it in Vivado, and I'll show you how we're going to open it in Vivado, and look, not only would you see the existing design that you had in your Vivado platform, but you would also see the additions that Vitis has added in as well. So hopefully we're nearly downloaded as well. I'll take a few minutes to look through the questions that we've got here. There's quite a lot of good questions. There's quite a lot of good questions coming in. So people asking about how to define specific bit widths, you know, and we're saying go away and, you know, the Vitis documentation provides you all that information that you need. There's elements about, you know, we've got Andy asking, one of the Xilinx guys just replied back to a question about how we actually measure power consumption and how we can measure power consumption in the Xilinx FPGA. So it's obviously downloading quite a large element today, or everybody at once. So all of a sudden, Xilinx has got 400 people requesting to pull from GitHub. So somebody's asked about the Vitis AI image. How big a area of RAM is, how big a hard disk space is needed, and you need a fairly large. Actually, the Vitis AI image is not that large itself, that you don't need a huge amount. But to actually install Vitis as we've done today, you'll see that you need quite a large. I think it's about 40 or 50 gigabytes that it takes up of memory space on there. So you can, it is possible if you remember back, so while this is still downloading, if you remember back to my area here, you can debug the kernel, and you can debug the kernel in different modes as well, in different waveforms. So that allows you to run through there and pull that up for the questions that it'll be asking. Somebody's saying, can the DPU be instantiated on the 7020? I don't think I've ever tried it, but I think maybe you could probably get, and hopefully one of the most, especially Xilinx guys knows the answer to this, but I think probably you could get one of the smaller DPUs on. You could get probably one of the smaller DPUs on there as well. Okay, so now we've finally got it all downloaded. If we take a look under the directory, you'll see that we've got you'll see the model zoo. So the model zoo I was talking about has been pulled down. You'll see the Alveo instruments. You'll see the Docker, because obviously we use Docker for Xilinx Vitis AI. You'll see some documentation as well. You'll see everything. You'll see the Vitis AI library. You'll see the profiler, the quantizer, and everything we need to get going and get up and running with that. And that's one of the really exciting elements that we've got. What we're going to do, we're going to take a look under this DPU TRD, and under here we're going to look under the project, and this gives us the ability. These are the projects that give us the ability to pull in the DPU using either a Vivado flow or a Vivado flow or a Vitis flow. And what we're going to do is we're going to pull in the Vitis flow. And this is really quite simple. It literally takes a few minutes to do this and run through this. So we're slightly ahead of time. So if anybody's got any questions, feel free to keep popping them in the questions area. So if I click here on dpuconf.vh, so this is the file. If you've ever taken a look at the Xilinx DPU, and there are some links at the back of the slide deck to the Xilinx DPU, this is the file where you can see the different configurations of the DPU and actually define which version of the DPU you want to use. So in this instance, we're going to use the 4096. This is how we can configure whether it uses Ultra RAM or not. Now, because we're targeting a ZCU 104, which has got Ultra RAM, we're going to leave these designs not unchanged. So we're not going to make any changes to this, because I'm just again showing you the capabilities, the flows, and how to do it. So you can see here, you can change the URAM if you want to. We can change the RAM usage option between high and low. We can change the channel augmentation. We can change the depth-wise conversion. A whole lot that we can make and change, and we can work through there. Whether we want to have whether we want to use a high number of DSPs, or whether we want to enable it for low power, and whether, as somebody was just asking the question, whether we want to run through and target the MPSoC, or whether we want to target the Zinc 7000. So we're going to target the MPSoC today. Now I'm going to click close on that. Now, if you want to configure it, maybe you want to make some changes to that, you can double click on the file. So someone's asking if we need to make DPU config file changes for the Ultra 96 V2, and I don't think you should. I think it should compile okay as it is by default. It should ignore the Ultra. I think it should ignore the Ultra RAM, so it should be fine. We also have the project configuration file, and this tells us about the interface that are available to connect to it. So you can see actually in this example, it's going to put in 2. If we generate this through, it's going to put in 2 actual DPUs into the system. It's going to create us 2 DPUs, and the DPUs are going to be connected to these interfaces, and these are the clocks that are going to be connected. So if you remember, the DPU needs if you've ever read the DPU reference material, it needs a clock, and it needs double that clock frequency as well. So we give it 300 and 600 megahertz to both of the clocks. We don't need to make any changes to this. What we're going to do is we're going to go back to that Vitis directory here. We're going to open back up our terminal window. We're going to export the system path, so where our platforms live, and this we're going to export this because it's in the SDX. We're going to use the SDX, not DSX. We're going to export the SDX platform variable. We're going to give it the location. Now the location is under opt. It's not going to do it. So the location is, I'm going to cheat because the location, just to make sure I get it correct. The location is under opt, Xilinx, platforms, and actually I'm going to give it this one. So this is the file. This is the file I actually want to use. So this is the file that this is the platform that we want to use. So I'm just going to do. Hopefully that's going to come through. Paste, and then it is the Xilinx. So that's the platform directory that we're going to use. So I'm targeting the 10, hopefully the 104 platform. I'm going to hit enter there, and then I'm just going to hit a really simple command: make binary container _1 /DPU .xo. So this is going to build a kernel image, the acceleration element that we need to use using Vivado, using Vitis HLS. I'm going to put in there that the device equals ZCU 104. Hopefully that's all correct, and I'm going to hit enter. The reason why is because I'm not in the right directory. I did this earlier on, so I need to do cd ls, cd Vitis AI, cd DPU. What's the next one? Project, cd project, cd Vitis. And then I can run that command again. And what we'll see is the make file runs through. And if and it'll take maybe it shouldn't take too long actually to run through. I'm going to go back to home, back to the DPU, back to the Vitis, back to the DPU TRD, back underneath the project, back underneath there, just so as we can see what's going off. You'll see it running through, and it's really quite quick to compile and do it. Hopefully we shouldn't get any errors at this point in time, and it'll pop through and give us everything you'll need. You'll notice that we've got some new directories that have appeared, and you'll notice under the that binary one container we've got this XO, this kernel image. So now we've got this, what do we want to do with it? So what we're going to do is we're going to come across to the Vitis IDE, and we're going to instantiate it in our design, and we're going to ask it to accelerate. Now we're not going to do a emulation or we're not going to do a software emulation or a hardware emulation with it. We're actually going to click on build and watch it build through to the end. We're not actually going to click on build and watch it build through to the end because it's going to take 30 or 40 minutes. Once I've got it all imported and ready to go, I'm going to open another project that pre-exists that I did this afternoon in the best Blue Peter tradition, if you're British. Here's one that I did earlier, just so as I can show you what it looks like in the end and how we'd use it. So what we do here is we click on the DPU system that we've got. We click on our source element here, and we say we want to import sources. And then we browse to the directory that we've just put this in. So the DPU for the USA, the Xilinx AI, it's under DPU TRD, under project, under Vitis, and then it's under binary container 1. So we click OK on that, and that's the path. And then we just say we want to import the XO file, and it's going to get put into the source code area. So with that, we can click on finish. Somebody in the comments is laughing at me making reference to Blue Peter, but it's true. It's literally here's one I created earlier. I also created it earlier just in case we had any issues or sort of live issues while the webinar was going off. So if we take a look under our source, we'll see the DPU XO. We'll see the DPU XO there. And what we can do then is we can literally go to the add hardware function option. So if we tick add hardware function, we'll see it list, and it will list all the hardware functions in our design that we possibly could add into here and run through. We've got this DPU, and there's the only one in our design. It's all nice and simple. We've put no software in or anything in it yet. And we're just going to click OK, and you'll see that we've then got this accelerated function here, which we can then go away and implement. If we change this to hardware, we can click on build, and it will build through, and it will show us the final the final results will come through, and it will give us a design that has got the processing system and it's got the DPU, or actually in this case 2 DPUs in the fabric. Now, if I just switch back, I want to show you a few things that happen post build, and I don't want you to have to wait 40 minutes or so. So I'm just going to change my workspace to the live one, which is one I did earlier on. So it'll take a few seconds while Vitis closes down and then reopens up again in the new workspace. Okay, so you can see this. This has come up, and this one actually was built this afternoon, hopefully. So what we can see once we've done this, so we can click on our lab on our DPU system. It's still thinking a little bit, obviously. So we could click on the DPU system. Maybe actually I can even show you the log if it came up from the hardware build. Maybe not. DPU system hardware. No, there's nothing. But what we can do is we can right click on this. So we can go to the Vivado project here. So we're in the DPU project. We can click on Xilinx. We can go to Vivado Integration. And why doesn't it want to open the Vivado project? I did build this. I swear I built it this afternoon. Open. And we can go to the Open Vivado project now. I've clicked on it. So click on Open Vivado. It's going to give us this binary container one. We'll click on OK. And you can do this, of course. This is not just for the DPU that you're seeing. You can actually do this on any element of the design that you want to do, any accelerated function that you want to do. If you want to see what it looks like in hardware, so you can run through this, and it'll take a few seconds, and hopefully we will get Vivado opening up. We can see it opening up now. So somebody's having some issues with running it. Don't try to run it in the hardware emulation. Make sure you've set that option. Make sure you set this option here, the active build configuration to hardware, and click build. But it will take a little time to run. It will take a little time to run through. So once we've done that, we can actually see this in Vivado. We can come through into Vivado now. You'll see Vivado's open. You'll see we've got the base wrapper open. And if we double click on this hardware, on this block diagram, then we can pop this out. And what we'll see here is we can see the implementation of the DPU. So we can see the DPU here. We can see it connected via the AXI, via this AXI Lite interconnect. So we can see the control elements to this the AXI Lite. So this is how you control and this is how the software will control and configure the DPU. And then we've also got these high performance outputs that are coming out of the DPU that are running into the Xilinx processing system, so into this slave interface here. So this is how the DPU would get information, get its source data, its application, to process and execute, and give us that really nice acceleration into the programmable logic. Now, what you can also see, this is quite interesting. You can see the interrupt, obviously. You can see the interrupts being brought out and worked into the interrupt system. So you can get an interrupt from the DPU when it's ready. You can also see all the clocking systems that have been put in place. So the 7 clocks that are available in this platform. You can see the processor system and the processor system resets that are associated for each one of these. And you can see the verification IP as well that gets dropped in there. So it's created a really comprehensive Vivado block diagram, and it has gone away and it has implemented this as a project. So if we click on the project summary, no, we won't see anything. We can see the results back here in Vivado, sorry, in Vitis. So I can see under this hardware element here, if we expand the hardware element, we can see everything that we need. We can see all the hardware. We can see all the hardware build containers and everything. We've not got a SD card image because actually, when we build this, there's no software. There's no system software being created at any point. Yet. But if we look under the this network, we see the where's it go? Link, Vivado, VPL, and under the project, and then under the project sources, and under so that can then use as an element. So I think I just dropped off for a second, but this gives us that element to be able to run through and see the see what we've put in the hardware there. So we can see all the different elements of our design. We can see it all nicely and implemented in our design. And here we can see the hardware handoff file. If we go all the way up and find that hardware handoff file again, as I was saying before, I think I just got disconnected temporarily. The hardware handoff file is what you'll use when we pull it through into Vivado, into the Vitis AXI and into the Vitis AI tool. Into the Vitis AI tool. We'll pull that into Vitis AI tool, and you'll use that to configure your Vitis AI applications and create your applications that you can then run on this DPU. So that really brings us to the end of it. We've got about 5 or 10 minutes left for any questions. So if anybody's got any questions, I will try and just run through them now. I'm not sure why the audio dropped off, so apologies briefly about that. We'll be making this all available so as you can take a look at it in your own time as well, and you can run through it. Obviously, we've got the labs that are available on GitHub, so as you can download them and work through them in your own time. And we've also got the slides. We've put the slides up there. My email address is at the front of this the front of the pack as well. So if you've got any questions, if you've got any challenges, if you hit any blocks, please feel free to reach out and talk to me. Drop me an email. I'll try to get back to you and help you the best I can. But I think what we've done today is, I think we've had, just to quickly summarize, is I think we've kind of had a bit of a whistle-stop tour through Vivado, through Vitis, and how we can create Vitis. So we've really run through the elements of what the tool is, how we can use the tool, how we can look at bottlenecks and how we can optimize the bottlenecks. We've looked at how we can create projects, how we can use software emulation to debug and get our algorithms right. We've looked at how we can use hardware emulation to make sure that we get our performance right and we get everything that we want in the performance that we want in our programmable logic. We've also then looked at how we can create a DPU and how we can put that deep learning element within our design into there using Vitis. And now it gives us the ability now that we are in a position that we can go forwards and you can start creating your own applications. Now, obviously, I want you to create your own applications, and I'd like to hear about your own applications, and I'd like to hear what you do with it. If you want to drop me an email, or if you want to create a project on Hackster or something to showcase what you've been doing, then I'd really quite love to see what you get up to. So I'm going to take a look now. I'm just going to take a look at the last few of the questions that we might have. Just to scroll up to the top of the questions. So somebody spotted my slide. Here's one I made earlier issue. So somebody was asking about, I instantiated 2 DPUs, and I did. But in the example I showed you, where I said I'd recompiled it, I actually only had one. So it was only when I first implemented it, it was only compiled to have one DPU in there because I was making some changes to the application to get it all up and running, and I wanted it to run through quite fast. So I only had, in the example I showed you when I switched workspaces, there was only one DPU in there. So Mendingus is asking about what's the best way to add in a DPU into a Vivado project, because the Vitis TRD is an empty design. So it's actually quite simple to take you can take the IP blocks from, let's just go where we are. So you can take the IP blocks somewhere, there's the DPU IP. So you can take the IP blocks and you can use this, you can pull this component in just as you would any other component in your Xilinx Vivado flow. You can pull that in, you can add that into your Vivado design, you can then connect it up to the AXI interfaces, provide the clock interfaces that you want. And if you want, actually, I think I've got a MicroZ Chronicles example that shows that, and it shows you how to implement that and get that up and running. So someone's asking, actually, we've not touched on it a lot today. Someone's asking about microblaze projects and is it worth it with Vitis? And of course it is. Of course it is. You know, Vitis is a multifunctional tool that allows us to work for AI and at the edges, and allows us to work with accelerated and edge applications. And microblaze is really still quite powerful. You know, I can't tell you how many clients come to me and I do work for them that involves microblazers or simple ARM M1 and OM3 applications in programmable logic devices, because sometimes you need that sequential, that software type flow and basis that it comes. So I've not touched on it today, but in Vitis you can do everything that you could do in SDK with the microblaze. So you can create applications, create bootloaders, create second stage bootloaders, do all the debugging, just as you could in SDK. Only there's a few nice additional elements thrown in as well. So somebody's asking about the performance channels for the hardware emulation being trustable. Obviously, it's not the final implementation because it's not got all the routing and all the delays in there. But I've found it to be a very good approximation, a very good indication of what you're going to get and how the performance is going to be at the overall system level. I think that's quite a good exploit. I think that's quite a good tool to have. And no matter what flow we use, you know, there's always a little bit of iteration once we finally put it on the hardware as well, just to do that final fine tuning. That's not just the case when you use Vitis. It's always the case when you do any development, be it software development or FPGA development or Vitis development. There's always just that last little bit. But what the tools do is they give you the ability to minimize that last little bit that you're going to have to do once you get the hardware done. So somebody was just asking if you can run microblaze with a DPU, and not really, I'm afraid, because the entire Vitis AI structure is set up around using the ARM 50, the A53s, the A5s, and the microblaze, powerful and capable as it is, it's really more for microcontroller applications than perhaps it is for high performance applications that you'd use an APU core for. So somebody was asking if they can use accelerated applications with the DPU and, say, for instance, XF OpenCV. And that's, of course, that's a really, really good question, actually, because while machine learning, AI is a really hot topic, it's only one small element of the overall system. And it's more likely that you're likely to need to have a image processing chain that can capture images and scale those images, process those images correctly to be passed through the image processing chip, the DPU. So yes, you can within Vitis, you can pull in the Vitis libraries, and you can pull in the libraries quite easily if you go to Xilinx libraries. I've actually got all the libraries installed, but if you don't have them, you just click this install option. You click this button here, which will install them all, and it will pull them down and install them all for you. And then you can start making use of the XF OpenCV. And literally, when you want to move functions into the hardware, you just add additional functions into this hardware, into this binary container that you're creating. So you can add in your let's say your median filter, your Sobel filter, and such like. You can add all that in, or your deep image processing. You can put it in there quite easily. So somebody just asked where in Vitis is the machine learning models, and that's all within the Vitis AI implementation that you downloaded. So that's got the AI zoo and has everything in there. What I would recommend is if you downloaded these slides, I've put some examples to some really, really great tutorials that Xilinx have provided on how to do that next step. So somebody's just asked, is it possible to, and we're getting to nearly the time, so I'll stop in a second. But somebody's just asked, is it possible to inject HDL kernels into Vitis? And yes, you can. If you've got an existing HDL module that you want to reuse, you want to use it as a kernel, you can do that. You can put a wrapper, you can essentially put a software wrapper around it and pull that in as a kernel into Vitis, just like you could with SDXL and SD SoC. So it gives you that really great functionality. I don't actually think I've written a blog explaining that. Maybe I'll put it on the list of things to do. But there's certainly one that I show how to do it for SD SoC, and it's not a million miles away, and not a lot different. So I think we're at the 2 hours now. We've run through it all. So unless there's any real other questions, I'm going to let you all go and enjoy the rest of your day or your evening if you're in the UK. If you want to run through it again, then I'm actually doing this same webinar, this same presentation again tomorrow morning at 9 AM UK time. So we'll be running through it all again. So if there's anything you've missed, you can catch up on the live stream, or you can come see me again in the morning. But thank you very much. It's been my pleasure to host you all this evening. And if you've got any questions, just please reach out. And I'm now gonna stop the webinar and go get myself a glass of water because I've been talking for such a long time. But I really hope you've all enjoyed it as well. And of course, Xilinx guys, thank you for answering all the questions, for supporting this, and thank you of course for sponsoring this and helping this to actually occur and go ahead. So with that, thank you very much, and I will end the webinar, and goodbye.